Speaker of the session is Ariel Chitan from Western University in Canada. She's a PhD student, and she will tell us how to disrupt disks around binary black holes and how that affects the accretion. Ariel, you're free to go.
Hello everyone. Thanks so much for having me, for inviting me here to come partake in this workshop. I remember I came to the first Phantom workshop in 2024. I was a complete and total noob with Phantom. I didn't know anything, never ran the code. I still am a very big noob with Phantom, but I just want to share a little bit about the project that I actually learned how to start in 2024. And where we have progressed with it. So I'm really fascinated by black holes, supermassive black holes and binary systems. And in particular, there's this one called OJ287, which I'm going to focus my talk a little bit about today. That's the main big black hole that we're going to look at. Again, I come from Western University, or University of Western Ontario, whatever you like to call it. So I'm coming from Canada, so my jet lag is a bit crazy. So forgive me if I ramble a bit, okay? So at the end of my talk, I would have liked to convince you that this OJ287 object that I am continuously talking about requires an ultramassive black hole, not just a supermassive black hole, but a black hole that is about 10 to the power of 10 solar masses. So that's incredibly huge. On the image that you see on the screen here, it's not OJ287, it is actually M87, which has a black hole around the same size. It has this beautiful jet coming out of it. OJ287 also has this huge astrophysical jet, but it doesn't look as nice as M87. That's why I didn't put it here, because it's a blazar object. So that object, the jet of OJ287 actually points directly toward us. So we don't see that beautiful structure that we see in M87. But OJ287 is undoubtedly one of my favorite objects that astronomers have ever detected. Why? Because just look at this beautiful figure on the screen here. This is a light curve, and if it's not big enough for you, I'll point it out. It starts in the year 1880. So astronomers have been detecting this light from OJ287 as far back as the late 1800s, especially astronomers in Finland, led by Slinpa, Valtonen, Harry Leito. They have been looking at this object. They have been collecting data, maybe on these like optical plates, whatever, as far back as that time period. Now, after like 50 years or so, after 100 years or so, they realized that when they look at this light curve, they saw these optical flares, these little peaks of light coming out. And they realized that there is some quasi-periodicity to these optical flares. Now, what they used to explain this quasi-periodicity of the light curve of OJ287 was that OJ287 was not just one single supermassive black hole out there in space, but it actually comprised of two supermassive black holes in a configuration kind of like this. So they said that, hey, there's a primary supermassive black hole, 10 to the power of 10 solar masses. There's this huge accretion disk around it. And then there's a secondary black hole that is very massive by itself as well. It's about 10 to the 8 solar masses, they believe. And is locked in a 12-year orbit around the primary black hole. And along its orbit, it punches through that accretion disk twice along its orbit. And they believe that it is this interaction of that black hole with the accretion disk that produces these optical flares that astronomers have been detecting. And it kind of explains the quasi-periodicity of these flares. So this is a bit of a messy figure, so bear with me. We're looking at the OJ system, just edge on. So that main red line is the disk, seen edge on. We have the jets going up and down. And that blue line, those blue circle lines are the orbital path of the secondary, what they think it looks like. So they have been able to time these flares extremely precisely using this binary model. So especially led by Valtonen in Finland, they have been able to say, okay, OJ287 should have a flare plus or minus a few days, and they detect it. So the model is pretty rigorous. Two things are important when they're predicting the timings of these flares. It is precession of the orbit, because we're dealing with huge masses. You can see from this figure here, and also from this plot of the orbital path of the secondary black hole with time, you see that lovely rosette pattern because the secondary black hole, the orbit just shifts by about 39 degrees per orbit. So it's pretty substantial. Another thing that I don't have up on the screen here is the disk response itself. Because when you have that secondary hitting the disk, the secondary is pretty massive as well. It acts to push down or pull up the disk as it makes its close approach to the disk. So there's two things that they have to calculate for being able to predict these flares. Precession, where is the secondary in its orbit, and two, the disk itself and how it's oriented. So why was I interested in looking at the OJ-287 system? Well, there was something that was supposed to happen in 2022, but it didn't happen. So astronomers predicted that in late 2022, there should be this optical flare coming from OJ-287, and they didn't detect any. So as I mentioned before, for the past like 50 years or so, probably even more, they have been very capable, very accurate, precise timing of these flares. But then there was one missing in 2022 when there should have been one. This led some astronomers, led by Kamosa et al., to say, okay, if we have our binary model of OJ-287 and we're making these predictions, but it doesn't match up, there is some failure of our model, does that mean that we need to reevaluate the model of OJ-287? Does that mean that we need to change things a bit? So they suggested that OJ-287, instead of having an ultramassive primary black hole at 10 to the power of 10 solar masses, they said that this primary should be about 2 orders of magnitude less, so about 10 to the 8 solar masses thereabouts. Of course, the figure is not always that clear because the other group of astronomers who are also involved in looking at OJ-287 had a little bit of a rebuttal on their own. And if you have some time, I suggest that you can go look at these papers going back and forth between the two groups of people. It's kind of funny and interesting. But Valtonen et al., which was the other group of astronomers, the ones who were involved in creating the model of OJ-287 in the first place, they said, wait, it's not that simple because OJ-287, it just was not visible from ground-based observatories in late 2022, meaning that maybe it wasn't that there was not a flare that happened, it's just that we didn't detect that flare from happening. Furthermore, they did not do the perfect disk calculations because they knew OJ-287 was not going to be quite visible. So yeah, it was just a matter of not being very precise in the timings and also not being able to see it properly from ground-based observatories. Whatever the case may be, this spiked my curiosity about the OJ-287 system, and I kind of wanted to dig a bit more into it. And this is where Phantom came into hand for me because I really wanted to look at the disk, that hydrodynamical simulations of OJ-287. So I really looked at 2 major simulations for this project. The first one was that high mass simulation, the really accepted model of OJ-287, where we have a 10 to the 10 solar mass primary and 10 to the 8 solar mass secondary. And then a second simulation where we drop the mass of the primary by 2 orders of magnitude to match that newer idea of the primary mass, 10 to the 8 solar masses. We keep the secondary as being about 10 to the 8 solar masses in this case, so it's kind of an equal mass simulation. And then we do a control simulation with just one supermassive black hole at 10 to the 10 solar masses. So whether you like it, whether you love it or hate it, we use a thin disk approximation for our black hole disk. So just for simplicity's sake, we use a very modest 500,000 particles for each of our simulations. And we include some general relativistic effects with the GR disk setup that is available to us in Phantom. So again, we're mainly looking at that precession of the orbit, which we're going to try to see in these simulations. Yeah, we use Phantom. So the main thing that I want to show you today is the 2 movies of the high mass simulation and compared to the low mass simulation. So on the left here, we have our high mass case, and we have the primary supermassive black hole, its accretion disk. And then we have the secondary in a little white dot. And I'm just going to let this movie play, and you're just going to see how it evolves with time, and then I'll explain what's happening. Sorry. Try it again. Okay, so the secondary, as we expect, it performs according to the OJ model. It orbits around the primary black hole. It punches through the disk, and as it punches through the disk, it generates these beautiful spiral density waves. And if you're paying close enough attention, or if you can see it properly, I guess, the secondary, the orbit, you actually see it shifting. It's precessing along with time. The disk itself also gets a bit thicker and a bit puffier with more and more impacts of the secondary black hole. And in some cases, you can actually see that the edges of the disk get really pulled upward and really lifted upward. So I'll just speed it up a bit. And this was run for over 250 years of this simulation, and the disk really holds up pretty well. In this still image, you can see quite nicely the spiral density waves that we talked about. Right. For comparison now, we're going to look at the low mass simulation on the right-hand side. So again, 10 to the power of 8 solar mass primary. We have the primary center here, and the accretion disk is a bit more face-on. One thing that I didn't mention to you before is that in both of these simulations, we keep the orbital period as being a 12-year orbital period, just to match up with the OJ system, the quasi-periodic flares. The masses are dropped, so things move a bit slower on the right-hand side. So I started at about 900 days, and we're going to see how this simulation evolves. So in quite a dramatic fashion, the passage of that secondary completely destroys and disrupts the disk of the primary black hole in our low mass simulation. It's not all that surprising because they're equal mass. The secondary, it steals some of the material and it kind of forms its own accretion disk. You'll see it just creeping back onto the screen there slowly. Systems like this may eventually evolve into those circumbinary disks that we heard a bit about this morning. But it's kind of clear to see that in these two simulations, the high mass simulation recreates that classical model, whereas the low mass simulation doesn't really survive the encounter at all. So the main thing that we saw was that in our high mass, the accepted model that was put under test, it holds up to that classical OJ287 system where we see repeated impacts of the secondary with the accretion disk for over 250 years. And this kind of lends into the length of time that we have been observing OJ287, which is over 130 years. So it must be that the real life object, if it is like this, it must have a disk that could sustain those impacts without being completely destroyed. So some more things from the high mass simulation that I'm going to focus on. So I'm going to look at the edge-on view of the disk. So we have in our high mass 10 to the 10 solar mass primary, the edge-on disk, the secondary is approaching in a white dot. It's going to hit the disk, pass through it, and then we see these plumes appearing both above and below the disk, which is very fascinating. And they last for about less than a year or so before the disk kind of smooths back out again. This is one of the main causes that astronomers attribute to the optical flares. What happens is the secondary punches through the disk, it shocks the disk, it heats up, the gases expand both above and below, so those plumes again. And as they expand, the optical depth decreases and you get that flaring events, which they have been detecting. Another thing which you would have seen in the longer movie that I just played, but you get to see it a bit more closely here, is the formation of these spiral density waves. So these spiral density waves, they last on a longer lifetime than the edge-on plumes. They last for about 2 to 3 years before the disk smooths back out again. So this can tell us a couple of things. Maybe the spiral density waves can help to boost the accretion onto the primary. Maybe it can affect the variability of the system. Maybe the longer term variability. So not just the optical flares of OJ287, but the longer variability in the system. Just to quantify a bit the vertical disk plumes that we're seeing, because that is one of the major things that they use to explain the flares. We also plot the fraction of particles that go above the twice the disk height. So you kind of notice right away that there's an upward trend. There's not a huge number of particles, but when we compare it to a control, there is also that kind of trend of the disk just kind of getting a bit more puffy with time, I guess, as it just evolves naturally. But what we're going to focus on is those little spikes in that fraction of particles that get thrown up. So what you're looking at, fraction of particles above twice the disk height on the y-axis, number of years on the x-axis. And then we have those red and blue stars just represent when we have an impact of the secondary with the disk. So we see very clearly, I don't know how clearly you can see it from there, but when we have a star in the graph, there's a bump in the number of particles, and then it goes back down. There's an impact and a bump, and it goes back down. So that's just a way that we quantify those edge-on plumes that we're seeing. Another interesting thing, and this lines back a bit more into the precession. So again, the secondary, as it's orbiting the primary, it impacts the disk twice. So what is the time delay between those two impacts? Because it's the impacts that we are interested in. So that's what you see on the y-axis, the time delay between successive impacts. On the x-axis is just the pairs of impacts. And you can see that the time delay between impacts, they go very short in some cases for about 1 year. And this relates to when the secondary's orbit is aligned in a more perpendicular way with the plane of the accretion disk. Of course, this is a cartoon just for exaggeration purposes. And then you have longer time scales between those two impacts when the orbit of the secondary is aligned more parallel with the plane of the disk. And it just takes a bit longer time for that secondary to move from one impact to the other. It also is kind of interesting to point out to you that where the secondary hits the disk, it'll have more of an impact in disrupting the disk. Because I don't show it here, but when it impacts the disk further out, it kind of pulls up the disk a bit more, which you may have noticed in the movie. But then when you have an alignment like this, the secondary is moving closer to periastron, is moving quite fast, and there's not much of a disruption of the accretion disk. I'm out of time. Okay. And then one thing that I was super interested in, because if you think about supermassive black holes, there's this big question about how do they get so massive? So one of the things we're looking at is the mass accretion rate onto our primary black hole. So what I wanted to do was to compare the mass accretion rate of that primary black hole in the high mass simulation to the mass accretion rate of just a single black hole simulation. So that's what you see on the y-axis, is that normalized mass accretion rate. On the x-axis, we have time in about 50 years. I just zoomed in so you can see it a bit more clearly. The red dotted line is 1 standard deviation above the average normalized mass accretion rate, so we can tell which ones are significant. And again, you can see those spikes where the accretion rate of the primary black hole in the binary actually gets bumped up to between 10 to 20% increase compared to the control simulation with just one supermassive black hole. And these quite follow nicely right after we have those impacts of the secondary. So it could be perhaps that the spiral density waves can help to push material much more onto the black hole. Or it could be the secondary hitting the disk and just throwing material closer in towards that accretion radius of the primary. Yeah. And then if we, in a similar way, if we look at the time difference between those accretion spikes, so what's the time between this spike and that spike? You can see something here. So on the y-axis, the time difference between those main accretion spikes. The x-axis on the right is just the number of pairs of accretion spikes, so to say. At the start of the simulation, there's a whole lot of accretion. We think it's just the simulation just settling in and normalizing after a bit. So that big spike that you see there, yeah, just ignore it for now. And then later on, as the simulation becomes more normalized, we see that the time between accretion spikes here They kind of lie along this red line, especially these few here. There are some here as well. But this red dotted line is a 12-year orbital period, the 12-year period of OJ287, where they see those bumps in the optical light and those flares. So it might be that these boosts in accretion if impacting some way those optical flares. So aside from just those edge-on plumes of the disk, the accretion could also play some role in helping to get these flares to occur. So I'll be fast with the current work, but I know there's one major question that you would have for me is because we did our lower mass simulation, but it's kind of an equal mass simulation. What if we had a different mass ratio with 10⁷ solar mass secondary black hole? So that's currently what we're working on. We're running a bunch of simulations where we keep the mass of the primary as being 10⁸, and then we're changing the mass of the secondary to a bit lower to see if we can actually recreate that OJ system with that lower mass secondary. And we have these. We changed the mass ratio, we changed the eccentricity, we changed the mass of the disk. And I'm going to show you very quickly, because I'm short on time, the most interesting one that we see so far. So this is simulation 3. I'm going to play this very quickly. So this is still in progress, what we're doing here. Let me just pause it for a second. Simulation 3 is a 10⁸ solar mass primary and a 10⁷ solar mass secondary with a 0.8 eccentricity. So what we're seeing is the secondary is approaching the disk. So it just passes by the disk. There is no interaction. But it does generate this spiral density wave within the disk. So in fact, all of our simulations, we don't see that classical OJ model with the secondary punching the disk, but only in 2 simulations, we see something like this happening. So that's currently kind of what we're looking at, and we're trying to get a paper on this out pretty soon. And then the last thing, I mentioned the disk itself, the disk response as a secondary passive phi. So the disk of that black hole, we see it gets pulled up quite a lot in some cases. So we're doing more high resolution simulations where we can zoom into those regions where we have that disk getting pulled up and kind of do some diagnostics on that. So the main takeaways I want to leave you with for this talk. We really favor the high mass simulation for OJ287, just because the disk survives repeated impacts for over 250 years, synonymous with the classical model. And in the lower mass simulation, the disk gets just destroyed after about 2 years or so it doesn't survive. We see those disk plumes and those spiral density waves very nicely in our simulations, which is very cool. And then we see the accretion rate get boosted 10 to 20%, helping to grow that primary supermassive black hole. And then our current work is just looking at changing the secondary masses and the disk warp. So I'll leave it on here, and thank you so much for your attention.
Thanks a lot, Ariel. If the presentation of Ariel sparked any question in your head, please raise your hand. Good to go. Josh, please.
So my understanding is the secondary is still kind of like a hypothesis here, right? About what's going on and causing these flaring events.
You mean in the actual object?
Yeah. In the actual object, right?
So I'll answer. There has been some papers out recently where they have detected like jet activity from secondary.
Yeah.
But some people think that it could not be that secondary jet. It could be something else. But yeah.
Okay. So like then if the mass ratio of 100:1 primary to secondary is what works well in your model, why not just drop the secondary? Even with the lower mass central black hole of 10⁸ solar masses, why not just drop the secondary then down to 10⁶? So you keep this 100:1 mass ratio that gives you kind of the nice, the model that seems to match observations.
Yeah, so we are doing those. So we're doing not 10⁶, but we probably could 10⁵ and 10⁸. I'm just trying to see if it does recreate that. So far it does not because at least with a 12-year period, it doesn't. Yeah. With the same setup, the same 12-year orbital period, same everything really, it does not punch the disk. like, yeah.
I was, thank you for the very nice talk. I was a bit confused why I was going to change to the secondary being a lower, sorry, to it being a lower mass, not secondary, the other one. It meant that the disk was basically entirely destroyed. I don't really understand why that's the case. Like if you change the mass ratio, but you've kept disk mass the same.
No,
You
the
kept-
disk mass changes.
Right, okay, so
Yeah,
this is.
so it's scaled with the mass of the primary.
Mhm.
So it's smaller, it's about 2 orders of magnitude, 3 orders of magnitude smaller than the disk of the higher mass simulation.
Okay,
Yeah.
so everything else was same.
Yeah.
Okay, thank you.
Any other questions? Yes, David.
Just curious, is there any chance we can get light curves from this? Because the way you detect them is like flux.
Yeah,
So
that's an amazing question. That's something I really, really want to do, is to get like curves from it, because you kind of want to see matchup to observational. It's a bit difficult to do because it's like in a GR regime as well. So, but yeah, definitely would love to have like curves from this object. But we have tried it a bit, but the luminosities have been quite high, a little bit unrealistic for now, but it's something that we'd like to do. Yeah.
And just to comment on that,
Yeah, we have.
is there, I mean, do you have any idea in OJ where the optical emission is coming from? Because like in tidal disruption events, that's like half the story is understanding where the optical is coming from. Like I assume the observations are mostly optical, but you must have X-rays as well.
So it's mostly optical. That's really only, I think I've seen one paper where they did multi-wavelength observations of it. I think in some mid-IR there is some fluctuation as well. So
Do you know, is there a good understanding in the literature of where that's thought to be coming from in OJ?
yeah, it's thought to be coming from the disk loops. If that answers your question.
So that's the model for what produces the optical emission, is the disk plumes.
That's what they're thinking. Yeah.
Any question? Yeah, some, which is that your orbit is misaligned, right, compared to the disk.
Yeah.
And so that means that the orientation of the disk is changing with time. And if you change the disk orientation with time, you also change the angle of the jet. The disk is like panel. And so my question is to see, I see you're not seeing the jet itself, but can you see any wiggling, like if the jet is created from the line of sight?
Okay, so yeah, so that's a great question. It would be really nice to incorporate magnetic fields just to have some of that jet activity. There's a recent paper where they looked at OJ, including some of the jet as well. And you're talking about the jet wobble, right?
Yes.
Yeah, and the jet wobbles a little bit. As far as I'm aware, we don't do that in our simulations. But yeah, it is something that.
I'm talking about observations here.
Oh, the observations.
Because I know that in simulations.
Yeah,
When
yeah.
I incorporated it, but in the observations, I think it's a signature of that.
Jet wobble. I don't know if they've observed jet wobbles, but they have observed this secondary jet turning on at some point. Yeah.
You could predict the tilt. For example, there's some analysis routines that maybe would be good to discuss with Beck or someone to just measure the tilt of the inner disk.
Yeah.
So if you assume the disk is mostly perpendicular, you could measure that tilt and use that as a proxy for the jet direction.
Take the last one then. I know that, well, I mean, like, from similar simulations, but much lower masses in binaries, the disk survival time is kind of dependent on the resolution you use. So if you increase the resolution a lot, do you think that your disk will survive more time than what was survived in the simulation? How do you think that will affect your results?
So we're currently running the high resolution simulations, and so far it looks to be about the same as the lower resolution simulations, at least the high mass binaries. Yeah.
Great. So if there's no more questions in the audience, we can thank Ariel and all the speakers of the session.